In this video, I want to have a look at some proofs that involve binomial expansions. So we're just going to do two examples. Our first one asks us to prove that the sum of the coefficients in a plus b to the power of n is equal to 2 to the power of n. So we're going to start by writing out the expansion of this binomial. So we're going to have a plus b to the power of n is equal to, now we're going to have n0 a n plus n1. A is going to be to the n minus 1, and we'll have a b to the power of 1. We keep going, n2, a to the n minus 2, b squared, plus, and we can keep going on all the way up. We don't know what n is, but it's going to go all the way up until we get to n. A will be to the power of 0, and b will be to the power of n. Okay, so that's our expansion, and we're trying to show that the coefficients are going to be equal to 2 to the power of n. So what we're going to do is we're going to let a equal 1 and b equal 1. So what that means is that this left-hand side then becomes 1 plus 1, so 2 to the power of n. And when we substitute a and b equaling 1 into here, everything except these combinations are going to be equal to just 1, because 1 to the power of anything is 1. So on this side, we're just going to have n0 plus this whole bit would become 1 as well. So we'd have n1, we'd have n2, and we'd have that all the way up until we get to nn. So that is all our coefficients added together equaling 2 to the power of n. Our second example asks us to use the expansion of 1 plus x to the power of n to prove this here. So n times 2 to the power of n minus 1 is equal to this. So we're going to start again by writing down that expansion. So we know that 1 plus x to the power of n is going to be equal to n0 plus n1x plus n2x squared plus n3x cubed plus, and it's going to go all the way up until we get to nn x to the power of n. Now, if you have a look at what we're aiming for, this gives us a bit of a hint as to what we're going to do to get there. So we've got this n1, and that's going to be on its own. This n2, we want to have a 2 in front of that. The n3, we want to end up with a 3 in front of that one. So what we're actually going to have to do here is differentiate both sides. So if I write that down, so if I differentiate the left-hand side, I'm going to end up with an n outside of 1 plus x to the power of n minus 1. So that's starting to look kind of like what we had. We've got the n in the front and the n minus 1 in the power. That's looking promising. Now this n0, that's just going to be a number. In fact, it's just equal to 1. When we differentiate that, it's going to be 0. When we differentiate this second term, we take the power of the x and we drop it down the front, and then we reduce the power. So that would be 1, and then n1. So we don't have to write that one down at the front. And then we'd have x to the power of 0, which we're just going to leave off. For the next term, we're going to bring that 2 down out the front. Then we're going to have n2 and x to the power of 1. And next one would be 3 n3 x squared plus all the way up, same process, until we end up with n x to the power of n minus 1. So what we're going to do now is let our x equal 1. So that's going to give us, on the left-hand side, it'd be n2 to the n minus 1, which is exactly what we want. Substituting in 1s here, all these x terms are just going to turn to 1. So we're just left with n1 plus 2 plus 3 n3, all the way up until we get to n. So having a look at what you're aiming for sometimes helps us figure out what the process is going to be to get there, but also having a look at those powers, because that's an n minus 1. We know that we do get that when we differentiate as well. So that's having a look at two examples of proofs that involve binomial expansions.